start from here. Okay, so what we call ILP is the integer linear programming. And when we call a problem, a model, an ILP model, it's because when one or more decision variables need to be integer. Okay, actually many of you have already implemented that constraint, the integer constraint in the case study. Like in chapter 3, you say, okay, you cannot produce like a partial club set and still count its profit into the total. Okay, so you set the integer constraints. So that becomes the ILP problem. Okay, and ILP occurs very frequently. Like when you schedule workers, you cannot schedule, say, 1.5 worker to work on a shift. Or manufacturing airplanes, how many to manufacture, we cannot say, okay, 1.5 airplane. So many of those places, actually in many of the problems we formulated earlier, it makes more sense to set those integer constraints. Okay, but because the way ILP solves is different, so we didn't introduce it earlier. Okay, but from now on, any problem that makes sense to add the integer constraint, you are expected to add this. Okay, and integer variables also allow us to build more accurate models for a number of common business problems. We'll start from a very basic one. Okay, I'll let you read this problem statement. And actually, you can formulate this yourself. So I'll let you read it and try to formulate yourself. I'll give you a few minutes. Okay, so this is called an employee scheduling problem. So the decision is to see how many people to assign on each of those shifts, right? Okay, so here, how many package handlers should be assigned to each shift? And they have an objective, which is to keep the total wage expense as low as possible. And the reason for this entire decision is because people on different shifts were given different wage rate. Okay, so if they have the same wage rate, then it doesn't matter. But here they have different wage rate. And to make this problem a little more complex is that on each of the day during the week, different number of workers are required. And for the workers that work on different shifts, they have different days off. So you really need to think about, okay, for example, if someone is assigned on shift 1, which day of the week can this person cover? So for example, if that person is on shift 1, he or she is off Sunday and Monday. That means he or she will only be able to cover Tuesday, Wednesday, Thursday, Friday, and Saturday. Okay, same for person assigned to shift 2. Then this person will only be able to cover Wednesday, Thursday, Friday, Saturday, and Sunday. Okay, so by determining how many people to assign on each of the shifts and add up the number that have each day covered, we need to meet those requirements here. Okay, so with this hint, so this is the basic information. So what the decision variable should we use? Okay, number of workers per shift. So we can put, say, x1, x2, x3, x4, 5, 6, and 7 here to be, so will be xi, right? Number of workers on shift I. Okay. Then the objective function would be, we want to minimize the total wage expense, right? So it depends on the number on this first shift. Say, okay, the X1 number of people on the first shift, wage paid will be this one. Okay, so you sum up. It's a sum product of the X and the wage rate. Okay, which is easy. So X. And so let's just put the so we define the xi's, okay, and then the objective function would be to minimize x1 plus 705 x2 plus 705 x3 705 x4 plus 6 plus 655x7. Okay, then let's think about the constraint. The constraint is to meet the worker required. So that means the number of people workers working on Sunday. Okay, need to be greater than or equal to the number of workers required here, right? So that's the right-hand side. So the left-hand side, let's decide, okay, who are covering this Sunday? Worker from shift 1 do not cover it because they have Sunday off, right? Okay, but the workers from this second shift will cover because they have Monday, Tuesday off, so they will cover Sunday. Okay, so that's x2, x3, 4, 5, 6, not 7, right? Because on shift 7 they have Sunday off again. Okay, so it will be x2, 3, 4, 5, and 6. Okay. Then with the same logic, we can write out the constraints for all the other 6 days. Okay, so for example, for Monday, the right-hand side will be 27, and we look at workers from which shifts will cover Monday. So this is off, right? So it would be from 3 to 7, right? So I goes from 3 to 7. Okay, greater than or equal to 27 here. Any question here? No? Okay. Then for Tuesday, we'll just do 4, 5, 6, 7, and 1, right? Don't forget to go back to the top. Okay. Then Wednesday, we will have 5, 6, 7, 1, 2. Okay. So I won't write all of them here now. And you don't need to copy because they are on the slide. So I'll post the slide. So these will be our constraint. And we'll add non-negativity and integer constraint for like this. Okay, so xi greater than or equal to 0 and xi's are integer. Okay, so this is the way to set the integer constraint. You specify xi's are integers. Okay, I found one student in homework 3, in defining the model, it says a non-negativity constraint. You don't write that as a math expression. Okay, you need to put xi greater than or equal to 0. I know what you're talking about, non-negativity, but if I ask you to formulate the math model, you need to write in the math word, in the math language. Okay, so it should be xi greater than or equal to 0 here and are integers. Okay, so this is the constraints for this problem. And
question, the zeros in there, do we want to include those inside of the problem, or is it
you don't have to include them. Okay. No. I put them here just for the model formulation, the Excel part. Okay. But I have a question here. Since the right-hand side, okay, those values, these are the number of people to to have, right? Those are the required number of people. Why do we use greater than equal to? Why not just use equal to? What's that?
Because we don't want to limit the
Okay, we don't want to limit the feasible region. Okay, we talk about this from the beginning of chapter 3. Okay, and this is the place where I want to emphasize it, because if we have strictly equal signs for this problem, you may not be able to find the feasible solution. Okay, we can try this. I have this model here on the Moodle side. If you want to try, you can download it. It's the week 9 class resource. But if you are pretty slow, then just look at me demonstrating. Okay. Okay, so here I have this model here. The model setup, that's something to learn too, but it's exactly what I have here. So Caleb asked, should we include those zeros here in the model? In this handwriting model, we don't need to. Okay, for example, here you can just start from x2 to x6. You don't need to include x1 and x7. So I put them here because the setup here in this table here, these are the coefficients. Okay, so I just set up them like this way, and so it's the sum product of let me see. So these are the decision variables if it's if it is okay, so we'll look at so here with those coefficients, and so the left hand side, those red ones represent what I have here. So it will be the sum product of those coefficients with your decision variables. Okay, so sum product of this column and this column. So with that, and also the total wage will be sum product of the wage column and the scheduled worker column. Okay, then what I want to do is to test. So let's go to addings. So objective will be this one, minimize the total wage. Variables will be the decision variables here. Oh, sorry, should be okay. Constraints. Okay, so let's see. First, I'll just add the constraints. Those decision variables need to be integers. Then, here. The left-hand side need to be equals to the right-hand side. If we just set equal to and non-negativity, ILP, and solve. See what happens. You need to read this message here. Okay, solver could not find a feasible solution. Okay, now let's go back to change this constraint to be greater than equal to. Click OK and solve. Now solver find an integer solution within tolerance. All constraints are satisfied. Okay, and if you look at here, so let me just show you something here. I have an integer optimality that's 0.05. This has something to do with the algorithm that we use to solve the ILP problems. Okay, this 5% here means that once the solver finds an integer solution that gives an objective function value that's within 5% of the objective function value of the model without an integer constraint, then we can stop searching for the optimal solution. Okay, so here if I change this back to 0, 0, then that means I request a solution that's the optimal. Okay, if it's a 5%, that means okay, maybe there will be another integer optimal solution that's like say 3%, which is better than the one I have here. Okay, but here if I set as 0%, solve. Okay, and then you said solve find the solution. All constraints and optimal conditions are satisfied. Did you notice the message is different, right? Here it says, okay, the optimality conditions are satisfied. Just now the message is saying, okay, let's go back to that one. So remember this one, okay? And go back to, okay, return. Go to options. If I say 0.05. Okay, find integer solution within the tolerance. The tolerance is the one that I set. The tolerance is at 95%, okay, or the 5% deviation.
But the solution is different.
Yeah, it can be different. It can be the same or can be different. Okay, if it find, this is saying, okay, it's within the 5% of the optimal. Within the 5% means it can be the same. It can be it's the 100. It can be 0% deviation or 1% or 2%, but the maximum deviation will be 5%. Okay, so that's what it's saying that suppose the optimal is 22. So let's go back again. Change this back to. So when you do homework for this chapter, I'll ask you guys to set your integer optimality to 0. Okay, because for the problems that I assign for this class, you will be able to find the 100% accurate. Solve again. Okay, so what we are seeing now is the optimal. So the total, that's the minimum wage would be $22,540. Okay, and if we set that option to be 0.05, which means 5%, then the deviation from this value, the objective function, the new objective function value deviation from this value will be no more than 5%. Okay. Is this part clear? Okay. I didn't want to cover too much algorithm for this problem because we focus on the application part, but this is something you need to learn. Okay. Okay, now we change the constraints from straight equal to greater than equal to. Okay. Now we find the solution, an optimal solution, feasible. Okay, and then you look at the solution here. So for Sunday, we get exactly the same number. Okay, Monday, Tuesday. You see, Tuesday we get more than what is needed, 4 people more. Okay, but why do we need those 4 more people? We probably need them to cover this one here. Because many of the people who work on Tuesday, they will cover, say, Wednesday, Thursday, Friday, or cover Sunday or Monday. Does that make sense? Because they work on a 5-day shift. Okay, so these additional 4 people here will be needed because they need to cover Sunday, Monday, or they need to cover Wednesday, Thursday. Okay, but here for Thursday, 2 more people need to be assigned, and Friday, 1 more people is assigned. And those additional people are needed to cover those other days that achieve the strict equal to. Okay, so we use this problem to demonstrate why we would like to have the constraint less restrictive to increase our chance to find a feasible solution. Okay, and if we can achieve strict equality for all the constraints in this problem, even if we have a greater than equal to sign here for the constraints, they will just turn out to be the same, okay, because we have the objective function, which is to minimize the total wage, okay, but we have to put the greater equal to sign to accommodate situations like this. Okay, so this is the first ILP problem, and this situation gets exaggerated, especially when we set integer constraint. Okay, sometimes without integer constraint, you may be able to find more feasible solutions. But with integer constraint, the feasible region is dramatically shrinked because maybe I'll just draw a little here graph here. Okay, for example, if the original feasible region for the problem without integer constraint is like this, okay, then if we add that integer constraint, say, okay, x1 and x2 need both be integers, then the feasible solution becomes some points. Make sense? The feasible region become those points because you require x1 and x2 to be integers. So those points, those points in between those integer values. So this will be, say, 1, 2, 3, 4. And here will be 1, 2, 3, 4. Only those integer values, those points representing both x1 and x2 are integer values, will be the feasible solution. Okay, as you can see, the feasible region shrinks dramatically when we add integer constraints. Okay, so we want to make sure our constraint is more accommodating. Okay, any question here? No? Okay, so that's the first problem.